Today we're going to look at identifying linear functions, being able to tell whether or not they are indeed a linear function. So first we're going to look at a definition. A linear function is a function whose graph forms, surprisingly enough, a straight line. Linear, a line, a straight line. So we're going to look at some graphs, and the first thing we're going to ask ourselves is the graph of function. From a previous lesson, we learned that a function is where the x does not repeat. The x is paired with exactly one output. Now, when it is a graph, we can identify whether it is a function using what we call the vertical line test. So if you see the red vertical line right here, I'm going to pull it across the function, the graph, and if it never touches more than one place on the blue line at a time, it is a function. That's called the vertical line test. Never did it hit more than one place at the blue line at a time, so yes, indeed, it is a function. So then we ask ourselves, it is a linear function. Is it a straight line? And of course the answer is yes, so it is a linear function. It is a function, and it is linear, therefore a linear function. Okay, here's another graph. First of all, let's figure out if it is a function. Again, you will see the red line right here where I'm going to do the vertical line test. So I'm going to pull it across the function. It never hits the function more than one place at a time. So that is a function. The x never repeats. And then we ask ourselves, it is a linear function. Is it a straight line? No, it is not. So it is a function, but it is not a linear function. Try it again. Again, you see the red line. We're going to pull it across to do our vertical line test. It never touches that function more than one place at a time, so it is a function. Is it linear? No. This happens to be quadratic because you see the parabola. So it is a function, but it is not linear. Okay, again, you see the function here. I'm going to try the vertical line test. And as you pull it across, you will notice that when you get to the function, it is touching all parts of the function at a time. So that is not a function. If it's not a function, there's no way it could be a linear function. Yes, it is a straight line, but it's not a function. So, not a linear function. Okay, let's pull the line across this for the vertical line test. It never touches that function more than one place at a time. So yes, it is a function, and it is a straight line. So it is a linear function. Sometimes we don't have a graph, we have a table. You can identify a linear function by looking at a table or a list of ordered pairs. In a linear function, a constant change in the x corresponds to a constant change in the y. What does that mean? We're going to look at the domain of the x values, and we're going to ask ourselves, how do I get from -2 to -1? Well, that's adding 1. How do I get from -1 to 0? Adding 1. How do I go from 0 to 1? And how do I go from 1 to 2? This is called a constant change because it was +1 on every one of them. So we have a constant change in the x. So now we check the y to see if we have a constant change. And it is written out here for you. To go from -4 to -1, you are adding 3. This is a +3 to get this value. To go from -1 to 2, again, you add 3. To go from 2 to 5, again, you're adding 3 and adding 3. So we also have a constant change in the y. So this is a linear function. If we were to graph all of these ordered pairs that are listed here, they would be a straight line. But you don't have to graph it in order to figure that out. You can look at the constant change in the x and the y. So here's one that's already written done for you. You can see that we have a constant change in the x values, +1, +1, +1. So we have our constant change in the x. We have +2, +2, +2. So we have our constant change in the y. So that is a function. Well, let's see if it is a function. Does the x ever repeat? No, it does not. So yes, it is a function, and yes, it is linear. So that is a linear function. It is a function because the x never repeated. It's linear because there was a constant change in the x and y's. Is this a function? Does the x ever repeat? 1, 2, 3, 4. The x, or the domain, never repeats, so it is a function. Is there a constant change in the y? Well, obviously there's not, because this was plus 3, this was plus 1, and this was plus 2. This is not a constant change. So it is a function if you were to graph this, but it is not a linear function. Is this a function? Does the x ever repeat? 0, 1, 2, 3, and 4. The x never repeats, so it is a function. Is it linear? Well, I can tell by looking at the x each time it's going up by 1, so that's good. Let's check the y's. To go from 2 to 4, you add 2. 4 to 6, you add 2. 6 to 8, you add 2. And 8 to 10, you add 2. This is called a constant change. So there is a constant change in the x's and the y's, the domain and the range. So here's my animation. It is a linear function. The x's are really easy to look at here. Again, it's 0, 1, 2, 3, 4, so we know it is a function because the x never repeats. Let's look at the, probably have animation for that too. Let's look at the y's. We have a plus 3. 4 to 7 is plus 3. 7 to 10 is plus 3. 10 to 13 is plus 3. That again is a constant change in the y's. And it would probably be good to note that this constant change has to be either adding a number or subtracting a number. And each time we are adding 3. So it is a linear function. Okay, again, our x values are very easy because each time it's up by 1. So it is a function because the x never repeats. Let's look at the change in the y's. 0 to 1 is plus 1. 1 to 4 is plus 3. At this point, I don't even really have to go any farther because it's not a constant change. It's not the same number being added each time. So this is a function because the x did not repeat, but it would not be linear if you were to graph it. Sometimes instead of a table, the order pairs, the group of order pairs called a relation, is just written like this, with the order pairs in a nice horizontal line. So first, to look to see if it is a function, we look at the x values to see if the x repeats. We have 2, 5, 8, and 11. The x does not repeat, so yes, it is a function. Is it linear? Well, let's look at the change in the x values. From 2 to 5, that's plus 3. From 5 to 8, that is plus 3. From 8 to 11, that is plus 3. So we have a constant change in our x values. Let's check the range, or the y values. From 4 to 3, that is subtracting 1. From 3 to 2, that is subtracting 1. And from 2 to 1 is subtracting 1. So we have a constant change in the x's and in the y's. The x did not repeat, so that is a linear function. First, is it a function? Let's check the x, or the domains. -10, -5, 0, and 5. None of those repeat, so it is a function. But is it a linear function? Let's see if there's a constant change in the x's. From -10 to -5, that would be plus 5. From -5 to 0 would be plus 5. And from 0 to -5 would be plus 5. So we do have a constant change in the x values. Let's check the y's. 10 to 4 is a -6. 4 to 2 is a -2. That's as far as we really need to go because we already saw that there is not a constant change. So it is a function because the x did not repeat, but it would not be a linear function. It would not be a straight line. Okay, let's look at the x values to determine whether or not it is a function. We have 3, 5, 7, 9, and 11. It is a function because the x does not repeat. Let's check for a constant change in the x values. 3 to 5 is plus 2. 5 to 7 is plus 2, 7 to 9 is plus 2, and 9 to 11 is plus 2. So we do have a constant change in the domain. Let's check the y values. 5 to 4 is subtracting 1, 4 to 3 is subtracting 1, 3 to 2 is subtracting 1, and 2 to 1 is subtracting 1. So yes, we have a constant change in the x values, we have a constant change in the y values, and it is a linear function. Now let's look at how to write a linear equation in standard form. You're always going to have an x value, you're going to have a y, and then you're going to have something that we call a constant. A constant is a number or a term without a variable. To write it in standard form, we're always going to write the x term first on the left side. Then we're going to have the y term second, right behind the x term on the left side, and then the equal sign, and then on the right side we have what's called the constant, or the number without the variable. So it's just a matter of rearranging things. Now, for it to be a linear equation, the x and the y, both this term and this term, can only have an exponent of 1. That means you will not see an exponent on the x, because when there's no exponent, it's an understood invisible 1. If there's any other exponent on the x or the y, for example, if you have x squared, that is not linear, that's going to graph quadratic. If it's x cubed, that would be a cubic graph. So, no exponents on the x and y other than 1, which is invisible. The x and the y cannot be multiplied together. There has to be an addition or subtraction sign between the x term and the y term for it to be a linear function. The x and the y terms cannot appear in denominators, in the exponents, or radical signs. And we'll look at examples of that here in just a minute. So let's look here. This is a linear equation. We have the x term, we have a plus sign, we have the y term, and on the right side we have what's called the constant. That is a good linear equation. There are no exponents other than 1 on the x and y. Now let's see an example of one that's not. Here, this one's not linear because right here we said that you cannot have, this one right here, you can't have the x and y being multiplied together. There you see x times y, so that would not be a linear function. This one is linear. It's not written in standard form, but I see an x term, I see a y term, and I see a constant. So that is a linear equation. It's not written in standard form. This one here would not be. Can you tell why? Because of this exponent of 3 on the x term. There can only be an exponent of 1. This one, you see an x term and you see a y term, so you might say, well, where's the constant? If there is no constant, which means a number without a variable, that means the constant is 0. And you can have a constant of 0. So this is a linear function. But this one is not because of this rule right here. You cannot have the x or y in the denominator. So you should be able to learn how to look at an equation and tell whether or not it is linear, if it would graph as a straight line. So here are the rules that we went over. Here is an equation. Tell whether this function is linear. If so, write it in standard form. Well, we have the x and the y. They both have an exponent of 1. The x and the y are not being multiplied together. And the x and the y do not appear in denominators, exponents, or radical signs, so that is linear. And to make it in standard form, the y is in the correct place because it is on the left side of the equal sign. All we have to do is move the negative, or the 5x, over here to the other side of the equation. Sometimes I call this jumping the fence. I call the equal sign a fence. So if this jumps the fence, you have to change the sign to a negative 5x. And why is that so? Because to move it to the other side, since it's a positive 5x, you would have to subtract 5x from both sides. It's doing that inverse operation. but instead of writing it out, I just know that when it jumps the fence, I change the sign. So I would have a negative 5x plus y, and this goes away because it jumped the fence to the other side. And on the right side, we have a negative 9. Okay, here's another equation. Is this function linear? Well, here you see the x variable as an exponent. They cannot appear as an exponent, so that is not a linear equation. Here is one. You see that the x and the y are being multiplied together. You cannot have them multiplied together according to that rule right there. So that is not a linear equation. Here we have an x term on the right side. We have a y term on the left side and a constant. So we have all three terms that we need. They're just not written in standard form, but it does check all of our, yes, it is a linear equation standards. Now, to put it in standard form, we just have to move some terms. The x term has to be the leading term. So when it jumps the fence, it becomes a positive 2x. We're going to keep the 2y on the left side, so that would be plus 2y. And now the 4, I'm going to erase all this so you don't see so many circles and arrows. Now the 4 has to jump the fence. It has to move to the other side, and it will become a negative 4 because you have to subtract 4 on both sides. And there it is, written in standard form. It's just a matter of moving terms from one side to the other, and when they move from one side to the other, they change their sign. This one, we have a y term, and we have an 8. There is no x term, so can it be a linear function? Yes, it actually can be. That just means that the x term would be 0. And when the x term is 0, you don't have to write it. So the x term and the y term may not be there, they just cannot be written in these different ways that we talked about. And it is in standard form. It just means that the x term, which would be right here, would be 0x. And since it's 0, we just don't write it. Here is one. We have an x term, we have a y term, but there is no constant. So can that be a linear function? It can. It just means, again, that the constant is 0. So we have the negative 7x on the left side where it needs to be. The y term needs to jump the fence. When we do that, we do a negative 2y. And then on the other side, since there wasn't a number, we just say plus 0. It's there, it's just invisible because it's a 0. Let's look at an example of linear functions here in the real world. Hans opens a new video game store and pays the gaming companies $5 for each video game he buys for them. The amount Hans pays is given by the function f of x equals 5x, where x is the number of video games being purchased. Graph the function and give its domain and range. So we have the number of video games that he purchased, and we have the cost. The cost is dependent on the number of video games, so we call the cost the dependent variable, so it goes on the y-axis. The number of video games is called the independent variable, so we put it on the x-axis. We have our equation. Now, in order to decide what domain we want to use for the x values, we notice that this is a one-quadrant grid, so we look down here at the x values that are actually on the graph. It starts at 0 and goes through 10. So when we choose our x values, we want to choose numbers that are off of that. You could choose 0, 1, 2, 3, 4, 5. You could go by 2s and choose 0, 2, 4, 6, 8, as long as you're choosing numbers that are from the graph. So I'm just going to choose the first 5 ones. And now we're going to plug it into the function, which was f of x. Remember, that's in function notation. It means the same thing as the y, just written in function notation, is 5x. So we're just going to plug 0 into x. So this would be 5 times 0, which of course is 0. 5 times 1, which of course is 5. 5 times 2, which is 10, 5 times 3, 5 times 4, and 5 times 5. Now we can graph all of these. So here we created our order pairs, 0, 0, an order pair of 1, 5, and so forth. So here is the domain written out. The domain are the x values, and the ranges are the y values. So here's when we graph 1, 5, 2, 10, 3, 15, 4, 20, and 5, 25. Now, before we draw the line, every time you put points, you think, oh, I got to connect the lines now. But now you have to stop and ask yourself, would this be a discrete graph, or is it a continuous graph? And we discussed this in a previous video. The discrete graph is where the numbers have to be exactly those numbers. In a continuous graph, it could also be all of the values between these two. So instead of $5, could he be paying $4.75 or $3.25? That's impossible because it's $5 per game. So this is what we call a discrete graph, and we would just leave the points and not connect the lines. Okay, so let's complete the table here. Here's the function. Let's see if it is a linear function. So when we're plugging in the domain here, we're going to plug in these numbers to this equation. A lot of times, you can plug it in just like this if you want to. I could plug in the -2 to x, and I could solve it this way. And now I know I have to add 2 to both sides, and y would be equal to 7. You can use the equation just the way it's written. Sometimes people like to put it in slope-intercept form first. So that would be putting the y on this side, moving the x to the other side, and this is just called slope-intercept form. And if you're familiar with slope-intercept form and this is more comfortable for you, you could put it in this, and now when you plug in the numbers, the opposite of -2 plus 5 would again be 7. You get the same answer, so you can plug it into the original equation, or you can put it in slope-intercept form. I'm just going to use the original equation. Let's plug in 0. When we plug in 0, then y is simply 5. When we plug in 2, then we have to subtract 2 from both sides. Then y would be equal to 2. Oops, I put 3 right there. Sorry, my mistake. Sometimes my brain goes to the answer too fast. Y is equal to 3. And now let's plug in 4. 4 plus y equals 5. We subtract 4 on both sides, so y would be equal to 1. So let's look at the x. This time it goes up by 2. This goes up by 2. This goes up by 2. So there's a constant change in the x values. This goes down by 2, down by 2, down by 2. So this should graph as a linear function. It is a function, and it is linear. So the order pairs were -2 and 7. I'm sure if I, whoops, sorry about that. Let's go back to it. We graph it, -2, 7. -2, 7 would be right here. And then we have 0, 5, which would be right here. And we have 2, 3, which would be right here. And 4, 1. Notice it is linear. It is a straight line. So we draw our line with our arrows. I hope this lesson helps in identifying linear functions.